The morning air across Intramuros hung thick with the smell of cordite and pulverized stone. It was February 23rd, 1945, and the ancient walls of Manila's Spanish colonial fortress walls that had endured 3 centuries of typhoons, earthquakes, and siege were about to face something entirely new. Behind the American lines, crews from Battery B of the 697th Field Artillery Battalion were making final adjustments to their weapon, a mechanical beast that demanded 22 men just to operate. The M1 240mm howitzer, nicknamed the Black Dragon. Inside the fortress, Lieutenant Takeshi Hayashi of the Imperial Japanese Navy's Manila Naval Defense Force pressed himself against reinforced concrete nearly 2 feet thick. The bunker had been designed according to Japanese military engineering principles, what the Imperial Army classified as a Class A defensive structure. Class A meant walls of 2 feet, 7 3/4 inches of steel-reinforced concrete, theoretically capable of withstanding direct hits from conventional artillery. Class B structures had walls 19.7 inches thick, Class C 11.8 inches, Class D just over 3 inches. Hayashi's position was Class A, the best his engineers could build. The walls had already absorbed dozens of impacts from American 105mm and 155mm shells over the past 2 days. The concrete bore scars and craters, but it held. What Hayashi could not have known, as he listened to the dull thunder of American artillery in the distance, was that the rules of artillery warfare were about to change. The Americans had brought up their heaviest field piece, and when a 360-pound projectile travelling at 2,300 feet per second impacts reinforced concrete, the laws of physics become unforgiving. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how the Black Dragon came to Manila and what it represented in the evolution of siege warfare begins not in the Pacific, but in the hills above Anzio, Italy, 14 months earlier. The M1 240mm howitzer entered American service in 1943, a direct response to the concrete fortifications of Hitler's Siegfried Line. During World War I, the United States Army had received several British 9.2-inch howitzers and been impressed by the French mortier de 280 modèle 1914 Schneider. About 330 of these French guns, in a slightly modified form, were built under license by the mid-1920s as the M1000 918 240mm howitzer, but by 1925, tests concluded the design was flawed. Work on a new carriage began in 1934, though actual development didn't accelerate until April 1940, when the war clouds gathering over Europe made heavy artillery a priority. The new howitzer was engineered alongside the 8-inch gun M1, both sharing a related split-trail carriage based on the design used for the 155mm gun. The 240mm version made quicker progress. It was standardized in May 1943 as the 240mm howitzer M1 on carriage M1. Production reached 315 units by 1945. The weapon's specifications were staggering. It fired a 360-pound high-explosive projectile, roughly the weight of 2 adult men at a muzzle velocity of 2,300 feet per second. Maximum range reached 25,225 yards, approximately 14 miles. The barrel alone required a 6-wheeled transport wagon. The carriage needed another. A 20-ton M2 truck-mounted crane was essential for assembly. Setting up the gun took approximately 2 hours, assuming the ground wasn't too soft and the crane didn't bog down. The 14-man crew had to dig a recoil pit, position the trails, install the barrel, check the hydraulic recoil system, establish the firing data, and prepare the ammunition, each shell hand-loaded, because nothing this large could be mechanized. The gun's nickname came from its first operational deployment. In January 1944, The 697th and 698th Field Artillery Battalions arrived at the Anzio beachhead in Italy. When the massive howitzers opened fire for the first time, Italian civilians witnessing the bombardment reportedly compared the sound to ancient legends of dragons. The name stuck. Soldiers serving the guns painted Black Dragon on the barrels, and the moniker appeared in official army publications. At Anzio, the 240mm howitzers proved their worth immediately. They were used for counter-battery fire against German long-range guns, and their accuracy exceeded all expectations. Artillery officers reported that the Black Dragon could not only knock enemy artillery out of action, but could destroy targets as small as German heavy tanks. One of their most celebrated achievements was helping to silence Anzio Annie, the infamous Krupp K5 283mm railway gun that had been terrorizing the beachhead. The massive American shells, dropping from high angles, found gun positions that German engineers had thought invulnerable. In Italy, the gun earned another reputation: bridge killer. The 240mm shell, striking a masonry bridge from 14 miles away, would not merely damage it, the bridge would cease to exist. At the casino front in February 1944, 12 Black Dragons joined 6155mm long toms. Despite having slightly less range than the long toms, the Black Dragon's projectile was more than 3 times as powerful. The howitzers demolished the bridge at Pontecorvo, cutting off German traffic from the south and west into the Liri Valley. During the final assault on Monte Cassino, after air bombardment had already damaged the monastery, 240mm shells finished what the bombers had started. One Army Ordnance officer wrote that the devastating firepower and incredible accuracy of the Black Dragon played a decisive role in the Italian campaign. Fifth Army commanders, initially skeptical about deploying such a heavy and unwieldy weapon, eventually dubbed it the most generally satisfactory weapon in service during 1944. Yet for all its success in Europe, the Black Dragon saw limited use in the Pacific theatre. The jungles of the South Pacific simply didn't have targets that justified bringing such a massive weapon ashore. The logistics were nightmarish. Each howitzer required 2 prime movers, usually M33 or M35 tracked vehicles converted from tank recovery units or tank destroyers. Moving the gun meant disassembling it completely, loading the 2 halves onto separate transport wagons, towing them to the new position, and reassembling everything. On soft jungle ground, even tracked vehicles bogged down. And most Japanese positions in places like New Guinea or Guadalcanal were either wooden coconut log bunkers that could be reduced with flamethrowers, or hidden cave positions where pinpoint accuracy mattered more than raw explosive. Power. Only 5 240mm battalions were deployed to the Pacific: the 543rd, 544th, 545th, 778th, and 779th. One battalion arrived in 1945, equipped with an experimental tracked carriage transport system, the T-16E1 gun transport wagon with 3 medium tank bogies on each side. But even with improved mobility, opportunities to employ the weapon remained scarce. Until Manila. The Battle of Manila in February 1945 presented a unique problem. Unlike the jungle campaigns, this was urban siege warfare against reinforced colonial architecture. And unlike the scattered resistance elsewhere in the Philippines, the Japanese commander in Manila, Rear Admiral Sanji Iwabuchi, had decided to fight to the death inside the city, transforming hospitals, universities, and government buildings into fortified strongpoints. General Douglas MacArthur had declared Manila an open city in 1942 to avoid its destruction. Now, 3 years later, he faced the prospect of reducing his former headquarters room by room, building by building. The centerpiece of Japanese resistance was Intramuros, the walled city, the oldest district of Manila, built by the Spanish in the 16th century. The walls were 16 feet thick in places, constructed of volcanic stone, and later reinforced with concrete during American colonial administration. Inside, the Japanese had fortified key structures: Manila Cathedral, Fort Santiago, government buildings, the old Spanish garrison. These weren't jungle bunkers. These were masonry fortresses with concrete reinforcements, firing positions calculated for interlocking fields of fire, and defenders who had been ordered to hold regardless of cost. The Americans tried conventional artillery first. 105mm and 155mm howitzers pounded the walls for days. White phosphorus rounds created smoke screens. High explosive rounds cracked the ancient stone, but the walls and the modern concrete Japanese bunkers inside them held. The Japanese defenders had stockpiled ammunition and supplies for a prolonged siege. Machine gun nests covered every approach. Snipers operated from cathedral towers. Civilians trapped inside became hostages, adding a moral dimension to the tactical problem. It was then that someone remembered the Black Dragons. Battery B of the 697th Field Artillery Battalion, veterans of the Italian campaign, had arrived in the Philippines with their howitzers. The guns were repositioned along the Pasig River's edge, offering direct line of sight to Intramuros. Spotters climbed to elevated positions across the river. Survey crews calculated exact ranges. Ammunition handlers prepared the 360-pound shells. Each round cost approximately $470 in 1945 currency, equivalent to several $1,000s today, but no one questioned the expense. 2 days of intermittent Black Dragon fire produced 2 vital breaches in the walls of Intramuros, but breaching the outer walls was only the beginning. Inside, the Japanese had constructed dozens of reinforced bunkers, each positioned to support the others. Lieutenant Hayashi's position was one of these, a Class A structure built into the foundation of a colonial building, with walls of 2 feet, 7¾ inches of reinforced concrete. The Japanese military had developed this classification system based on extensive engineering studies. Class A structures were designed to withstand naval bombardment and heavy aerial bombs. The walls were poured with high-strength concrete, properly cured, reinforced with steel rebar in a matrix calculated to distribute shock forces. In theory, a Class A bunker could absorb multiple hits from standard artillery before catastrophic failure. Japanese defensive doctrine in Manila reflected lessons learned across the Pacific. At Tarawa, Saipan, Peleliu, and Iwo Jima, American forces had discovered the terrible efficiency of Japanese bunkers. At Saipan, 4 steel-reinforced concrete defense installations larger and stronger than any previously encountered had constituted vital elements in the defense of Aslito airfield. Flamethrowers and light artillery had been used to no avail against these structures. At Tarawa, Marines had assaulted coconut log bunkers so well constructed and concealed that entire companies had been pinned down for hours. The lesson was clear. Japanese engineers knew how to build positions that could withstand punishment. The concrete used in these bunkers was usually locally sourced, mixed according to Japanese military specifications that had been refined over years of construction. In the Philippines, Japanese engineers had access to adequate materials: cement, aggregate, reinforcing steel. Filipino labor, both voluntary and conscripted, had built many of these positions during late 1943 and early 1944. One historical account from General Santos City described how bunker workers and Japanese soldiers had established cordial relationships during construction, sharing food and learning elements of each other's languages. But the technical specifications remained strictly military. The concrete walls had to achieve specific compression strengths. The reinforcing steel had to be placed at calculated intervals. Ventilation systems had to allow air circulation while preventing the porting entry of flamethrower fuel. Firing ports had to be narrow enough to prevent grenade entry, but wide enough for effective fields of fire. Inside Lieutenant Hayashi's bunker on the morning of February 23rd, these engineering calculations seemed adequate. The previous day's shelling had been intense, but the structure had held. Chunks of concrete had spalled off the interior walls from the impact shocks, and the bunker filled periodically with dust that made breathing difficult, but the walls themselves remained intact. The garrison had water, rice, and ammunition. Machine guns covered the approaches. In the Japanese military mindset, this was a position that could be held indefinitely, or at least until American infantry closed to assault distance, at which point the defenders would exact a terrible price. What the defenders did not know, what they could not have known from inside their fortification, was that the American artillery on the far side of the Pasig River had changed. The 105mm and 155mm guns that had been hammering intramuros for the past 2 days had been joined by something categorically different. At 7:30 a.m. on February 23, 1945, the bombardment plan entered its final phase. 4 battalions of 105mm howitzers, 3 battalions of 155mm howitzers, a single battery of 240mm howitzers, and a token battery of 107mm mortars prepared to unleash coordinated fire on Intramuros. The bombardment was scheduled to last exactly 1 hour, from 7:30 until 8:30, accompanied by salvos from Sherman tanks and M18 Hellcat tank destroyers positioned along the river. The 240mm crew went through their firing checklist with practiced efficiency. The spotter confirmed coordinates. The powder charge separate from the projectile in this separate loading ammunition system was positioned. 6 men operated the loading tray, a mechanical system necessary because the 360-pound shell could not be manhandled into the breech. The projectile was lifted, aligned, and pushed into the rifled bore. The powder charge followed. The breech block closed with a solid clank of interrupted screw threads. The gunner made final elevation adjustments, accounting for the distance of approximately 800 yards to the target close range for a weapon designed to shoot 14 miles. The gun captain gave the order. The lanyard was pulled. Inside the breech, the primer ignited the propellant charge. In the chamber formed by the obturator spindle assembly, powder chamber, rotating band, and base of the projectile, the burning propellant generated gases at tremendous pressure. This pressure overcame the initial bore resistance, and the projectile began its forward motion. As it accelerated down the 27-foot, 8-inch barrel, the lands of the rifling engaged the copper rotating band around the shell's base, cutting deep grooves that imparted spin. This spin, right-hand twist in all United States howitzers, would stabilize the projectile in flight, keeping its long axis parallel to the trajectory. The entire sequence from primer firing to muzzle exit occurred in approximately 15 to 25 milliseconds. The projectile emerged from the muzzle at 2,300 feet per second, roughly Mach 2 at sea level, trailing a jet of escaping gases that produced the characteristic boom of artillery fire. The noise and shock rolled across the Pasig River. The massive gun recoiled backward against its hydraulic system, absorbing the tremendous forces involved in launching a 360-pound object at supersonic velocity. The shell, now in independent flight, followed a ballistic trajectory. At close range, 800 yards, the flight path was relatively flat compared to the high-arcing trajectories used for maximum range. The projectile maintained supersonic velocity for most of its brief flight. Aerodynamic forces acted upon it. Gravity pulled it downward, air resistance slowed it slightly, and the spin imparted by the rifling kept it stable. The shell travelled through the morning air, invisible to the naked eye, faster than the sound of its own firing. From muzzle exit to impact took approximately 8 seconds. Inside Lieutenant Hayashi's bunker, there was no warning. Sound ranging the acoustic method of detecting enemy artillery by the noise of firing was a sophisticated technology that required arrays of microphones, recording equipment, and trained operators positioned kilometers behind the front lines. It was used for locating enemy batteries for counter-battery fire, not for warning individual defensive positions of incoming shells. Flash spotting, which detected the muzzle flash of firing guns, required observers with clear line of sight, and worked best at night. Neither system could provide tactical warning to a bunker under bombardment. Even if Hayashi had known the Black Dragon was firing, even if he had possessed perfect information about the projectile's trajectory, there was nothing he could have done. 8 seconds. The human reaction time to visual stimulus is approximately 250 milliseconds, a quarter of a second. It takes another second or two to process information and decide on action. Physical movement takes additional time. In 8 seconds, a person might dive for cover, take 3 running steps, shout a warning. But there was nowhere to dive. The bunker was covered. The bunker was supposed to be safe. The 360-pound projectile struck the reinforced concrete wall of Lieutenant Hayashi's Class A structure at approximately 2,100 feet per second. It had lost perhaps 200 feet per second to air resistance during its brief flight, but it remained supersonic. The kinetic energy at impact was staggering, over 150 million foot-pounds of force concentrated on the projectile's nose. Concrete is extremely strong in compression. When weight bears down on concrete, the load of a building, the pressure of earth, the material excels at distributing and resisting that force. Steel rods incorporated into reinforced concrete provide additional strength in tension, resisting the pulling and tearing forces that would otherwise cause concrete to crack and fail. This is why reinforced concrete makes excellent bunkers. The shock wave from an explosion compresses the concrete, but the material's strength in compression absorbs the force. The steel reinforcement prevents the concrete from being torn apart by the tension forces that follow the initial compression. But these engineering principles assume conventional artillery. A 105mm shell weighs 33 pounds. A 155mm shell weighs 95 pounds. These projectiles rely primarily on their explosive charges to create damage. They detonate on or near the surface, and the blast wave and fragmentation cause casualties and structural damage. Against thick, reinforced concrete, these shells create craters and spalling chunks of concrete blown off the interior surface by the shock wave, but they rarely achieve complete penetration unless the concrete is poorly constructed or the bombardment is sustained over many hours. The 240mm shell was different. 360 pounds of steel and high explosive, travelling at 2,100 feet per second, possessed such enormous kinetic energy that it functioned as a penetrator before it even detonated. The projectile's hardened steel nose punched through the outer surface of the concrete. The material that had seemed so solid, so reassuring, behaved under this extreme force like something brittle. Cracks radiated from the impact point. The shell's momentum carried it deeper into the wall, crushing aggregate, shearing through the steel reinforcement bars as if they were wire. The penetration depth depended on numerous factors: the angle of impact, the quality of the concrete, the placement of the reinforcing steel, the exact velocity at impact. But against a wall 2 feet, 7 3/4 inches thick, a Class A structure, the 360-pound projectile at 2,100 feet per second could penetrate completely before detonation, or it could lodge just beyond the wall's midpoint. Or, if the angle was oblique, it could begin to tumble inside the concrete, creating catastrophic structural failure before the explosive filler even ignited. The fuse on the 240mm high-explosive shell was a concrete-piercing fuse, a delayed action mechanism designed to detonate after penetration rather than on surface contact. This meant the explosion occurred inside or just beyond the wall, where it could cause maximum structural damage. The shell contained approximately 60 pounds of high explosive, typically a mixture of TNT and other compounds. When this charge detonated, it released energy equivalent to several hundred sticks of dynamite, all at once, inside or immediately behind a structural wall. The explosion converted solid matter into gas at temperatures reaching 3,000 degrees. The expanding gases exerted pressure in all directions simultaneously, what engineers call a blast overpressure. In the confined space within or just beyond a concrete wall, this pressure wave had nowhere to go except through the path of least resistance. The concrete, already compromised by the penetration, catastrophically failed. The wall didn't just crack, it exploded outward in both directions, hurling chunks of concrete, twisted steel reinforcement, and fragmentation from the shell casing at lethal velocities. The blast wave propagated through the bunker at the speed of sound in confined spaces, approximately 1,100 feet per second. It compressed the air inside the structure to pressures that ruptured eardrums, collapsed lungs, and caused internal hemorrhaging. The overpressure lasted only milliseconds, but in that brief time, it could kill through blast injury alone, even without fragmentation or thermal effects. Soldiers standing inside a bunker when a 240mm shell penetrated and detonated might die from the pressure wave before they could register the sound of the explosion. The fragmentation followed the pressure wave. Chunks of concrete weighing several pounds, moving at hundreds of feet per second, became deadly projectiles. Steel fragments from the shell casing, designed to maximize anti-personnel effect, filled the interior space. The reinforcing steel bars, torn from the concrete matrix, whipped through the air like jagged spears. Dust and pulverized concrete created an instant choking fog that made breathing impossible. The thermal pulse from the explosion, brief but intense, ignited anything flammable. For the defenders inside, there was no time to comprehend what was happening. The human brain processes visual information at a delay of about 50 to 80 milliseconds. The explosion occurred, the blast wave propagated, and men died before the neural signals from their eyes reached their brains. It was not death by gunfire, where reaction might be possible. It was not death by grenade, where there might be seconds to respond. It was instantaneous annihilation, the conversion of a defensive position from safety to death in less time than it takes to blink. This was the reality that Lieutenant Hayashi and his garrison faced when the Black Dragon fired. The Class A bunker, with its 2 feet, 7¾ inches of reinforced concrete, represented the pinnacle of Japanese defensive engineering. The specifications had been carefully calculated. The concrete had been properly mixed and cured. The reinforcing steel had been correctly placed. Against conventional artillery, the bunker would have held. Against aerial bombs of the sizes typically used in 1945, it would have provided genuine protection. But it had never been designed to withstand a 360-pound projectile traveling at 2,100 feet per second. The engineers who developed the Class A, B, C, and D specifications had based their calculations on known threats. They had test data from conventional artillery strikes. They had damage assessments from aerial bombardment. What they did not have was experience with super-heavy field artillery used at close range against fixed fortifications. The M1 240mm howitzer had been designed to attack Germany's Siegfried Line massive concrete fortifications built to withstand siege. Its use against individual bunkers in urban warfare was an improvisation, an adaptation of a strategic weapon to a tactical problem. The results were catastrophic. The February 23rd bombardment lasted a full hour. 4 battalions of 105mm howitzers, 3 battalions of 155mm howitzers, the battery of 240mm howitzers, and the battery of 107mm mortars fired in coordinated sequence. Sherman tanks and Hellcat tank destroyers added their guns. The defensive positions inside Intramuros, designed to withstand siege, instead faced industrial-scale destruction. Each 240mm shell that struck a bunker directly eliminated that position. Each near miss created craters and structural damage that made adjacent positions untenable. The interlocking fields of fire that Japanese engineers had so carefully planned became irrelevant when the bunkers themselves ceased to exist. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 8:30 a.m., the bombardment ceased. The smoke and dust began to clear. Two vital gaps had been widened into breaches large enough for infantry assault. The 120th Infantry Regiment and 145th Infantry Regiment of the 37th Infantry Division prepared to cross the Pasig River. A smokescreen that included white phosphorus rounds concealed their movement. Assault boats carried the first waves across. The men hurried past the abandoned post office between the wrecked Quezon and Santa Cruz bridges. Then they were inside Intramuros. What they found bore little resemblance to the fortress that had existed an hour before. Buildings had collapsed, walls had been reduced to rubble. The positions that had been bristling with machine guns and rifles were silent, not because the defenders had retreated, but because the positions no longer existed as fighting positions. Some bunkers had been completely destroyed, reduced to craters filled with rubble and twisted steel. Others had partially collapsed, their structural integrity compromised to the point where they offered no protection. The Americans advanced cautiously, expecting resistance, but the resistance that came was disorganized, sporadic, the actions of survivors, rather than a coordinated defense. The 120th Infantry Regiment's advance was led by L Company. Inside the walled city, movement remained precarious. The colonial edifices, like Letran University, still contained machine gun nests that had survived the bombardment. To the Americans' surprise, Filipino civilians were still fleeing from their Japanese captors, even in the midst of battle. The reality of the Battle of Manila was that the Japanese had taken hostages thousands of Filipino civilians trapped inside Intramuros, held as human shields, or herded into buildings that became mass execution sites. The Americans faced not just a military problem, but a humanitarian catastrophe. The use of the Black Dragon against Intramuros has remained controversial in historical assessments. The weapon was designed for fortress warfare, for reducing prepared positions from long range. Using it at close range in an urban environment where civilians were present raised questions about proportionality and necessity. American commanders argued that conventional artillery had failed to breach the defenses adequately, that the Japanese were using civilians as shields and executing hostages, and that prolonging the battle would result in even greater civilian casualties. The Japanese defenders, following Rear Admiral Iwabuchi's orders, had decided to fight to the death and to destroy Manila rather than allow its recapture. In such circumstances, the Americans contended, the quickest way to end the battle was the most humane. The numbers support grim conclusions regardless of perspective. The Battle of Manila lasted from February 3rd to March 3rd, 1945. Approximately 16,000 Japanese defenders died. American casualties included over 1,000 dead and 5,000 wounded. But the civilian death toll reached an estimated 100,000 Filipinos killed in Japanese massacres, caught in crossfire, or victims of the bombardment necessary to dislodge the defenders. Manila, the Pearl of the Orient, was left in ruins. Intramuros, the oldest district, was approximately 90% destroyed. The Black Dragon's contribution to this destruction was proportionally small but symbolically significant. It represented the application of maximum force against positions designed to be invulnerable. For the Japanese defenders who survived the initial bombardment, the experience was psychologically devastating. The defensive doctrine that had sustained them throughout the Pacific War, build strong positions, fight from prepared defenses, exact maximum casualties from the attackers had been rendered obsolete. At Tarawa, Saipan, Peleliu, and Iwo Jima, bunkers had made American advances bloody and costly even when the Americans eventually prevailed. Individual defensive positions had sometimes held for days, requiring flamethrowers, satchel charges, point-blank tank fire, and naval gunfire to reduce. At Manila, the Black Dragon demonstrated that there existed an artillery piece capable of destroying even the strongest bunker in a single direct hit. This realization spread through Japanese defensive planning for the remainder of the war. Reports from Manila filtered back to planners preparing the defense of Okinawa, scheduled for April 1945. The lessons were incorporated: build deeper, build underground, create tunnel complexes that could not be destroyed by single shells, no matter how large. On Okinawa, Japanese engineers excavated extensive cave systems, some capable of housing entire companies. The defenses included underground command centers, storage facilities, and medical stations integrated into the landscape. When Americans landed on Okinawa on April 1, 1945, they faced not concrete bunkers, but subterranean fortifications that could only be reduced by infantry assault, cave by cave, tunnel by tunnel. The evolution of Japanese defensive doctrine from concrete bunkers to cave systems represented an acknowledgement that above-ground fortifications, no matter how well built, could be destroyed by American firepower. It also represented a shift from static defense to elastic defense, trading space for time, withdrawing into prepared positions, forcing the Americans to root out defenders from increasingly inaccessible positions. The cost in American lives at Okinawa was staggering: over 7,000 killed, 32,000 wounded. The cost in Japanese lives was even worse: over 100,000 military deaths and as many as 150,000 civilian deaths. The battle lasted 82 days, from April through June 1945. The 240mm howitzer saw its final major action of World War II at Manila. The weapon's mobility limitations and the evolution of Japanese tactics made it less useful as the war progressed. After the Japanese surrender in September 1945, the Black Dragon was retained in the American arsenal but saw limited peacetime use. The guns were expensive to maintain, the ammunition was costly to produce, and the specialized training required for crews made them inefficient for a peacetime military. Then came Korea. On June 25, 1950, North Korean forces crossed the 38th parallel, beginning the Korean War. The initial North Korean offensive pushed United Nations forces back into a small defensive perimeter around Pusan. As the tide turned and UN forces advanced north, they encountered increasingly sophisticated Chinese and North Korean defensive positions. By late 1952 and early 1953, the front had stabilized into static warfare, reminiscent of World War I: deep bunkers, extensive trench systems, fortified hills. American artillery found that conventional weapons struggled against these positions. The Chinese, learning from Japanese experience in World War II, had built bunkers deep and strong, often carved into hillsides with overhead protection that could withstand standard artillery fire. In response, the U.S. Army brought 12 240mm howitzers out of storage. They were organized into two battalions, the 213th and 159th Field Artillery Battalions. The weapons went into action on May 1, 1953. The first round fired by Baker Battery of the 213th was aimed at a target atop a hill that aerial observers called the Donut. The shot was supposed to be ceremonial, a demonstration of the weapon's deployment. Instead, it struck an ammunition dump directly on top of the hill, triggering a chain reaction that blew part of the hill's summit off in spectacular fashion. The Black Dragon had announced its return to service. From May 1st through the armistice on July 27, 1953, the two battalions fired 5,043 240mm shells, weighing 163 kilograms each. The guns were effective against Chinese bunkers and cave positions that smaller artillery could not reduce. But the Korean deployment also highlighted the weapon's limitations. The guns were difficult to move in mountainous terrain. Setup time made them vulnerable to counter-battery fire. The ammunition supply was finite, the shells were expensive, and production had ceased after World War II. When the armistice was signed, the remaining ammunition stocks were conserved. By the late 1950s, the 240mm howitzer was becoming obsolete. Advances in rocketry and missile technology offered more efficient ways to deliver heavy firepower. Tactical nuclear weapons, introduced with the M65-2, a 180mm atomic cannon in 1953, changed the calculus of siege warfare entirely. The concept of reducing fortifications with conventional artillery seemed archaic in an era when a single nuclear shell could obliterate everything within a mile radius. The United States Army withdrew the Black Dragon from service as ammunition stocks were exhausted. Most of the guns were scrapped or placed in museums, but approximately 30 M1 240mm howitzers found a second life with the Republic of China on Taiwan. Transferred in the late 1950s, these guns were deployed on the frontline islands of Kinmen and Matsu, facing the Chinese mainland across the Taiwan Strait. Taiwan's use of the Black Dragon reflected the unique circumstances of the Chinese Civil War frozen in place. Kinmen and Matsu, located just miles from mainland China, remained under nationalist control after the communist victory in 1949. Throughout the 1950s, the islands faced periodic bombardment from communist artillery. In response, Taiwan fortified the islands extensively, carving bunkers and tunnels into the rock. The 240mm howitzers were mounted on rails inside hardened tunnels, allowing them to roll out for fire missions and then retreat inside for protection from aerial bombs and counter-battery fire. As of the early 21st century, some of these weapons reportedly remained in position, maintained but rarely fired. They served more as symbols and deterrents than as practical weapons, relics of a different era in artillery warfare, preserved against the possibility of a conflict that has so far not come. Taiwan occasionally conducted firing exercises with the old howitzers, partly for training, partly for demonstration, partly to remind observers that the weapons remained functional. But in an age of precision-guided munitions, drones, and cyber warfare, the relevance of a 1940s-era siege gun is questionable. The legacy of the M1 240mm howitzer extends beyond its service record. It represents a specific moment in the evolution of siege warfare, the point at which conventional fortifications became vulnerable to conventional artillery. For centuries, military engineers had engaged in a competition between fortification and bombardment. Thicker walls necessitated larger guns necessitated even thicker walls. The 240mm howitzer, firing a 360-pound shell at 2,300 feet per second, shifted that balance decisively. A Class A bunker, built to the highest Japanese engineering standards, could be destroyed in a single direct hit. This meant that static defense, the foundation of Japanese Pacific War strategy, was no longer viable against an enemy with sufficient artillery resources. This realization influenced post-war military thinking. NATO and Warsaw Pact planners, contemplating potential conflict in Europe, designed fortifications that were either so deep as to be effectively invulnerable or so dispersed as to be not worth targeting with individual heavy shells. The emphasis shifted from building impregnable positions to building numerous, redundant, and replaceable positions. Or, alternatively, to abandon static defense entirely in favor of mobile warfare, where positions would not be held long enough for heavy artillery to be brought to bear. The 240mm howitzer also influenced artillery development. The weapon's success demonstrated the value of super-heavy field artillery for reducing fortifications, but its limitations highlighted the need for improved mobility and faster setup times. This led to development programs for self-propelled versions, though the T-92 howitzer motor carriage, a 240mm gun mounted on a stretched Pershing tank chassis, was cancelled when only 5 prototypes had been built. The weapon would have been useful against Japanese bunkers and caves, but the war ended before it could be deployed. In the decades following World War II, the role filled by the Black Dragon was increasingly taken over by other systems. Rockets could deliver comparable or greater explosive payloads with better range and without the logistical burden of moving a multi-ton howitzer. The U.S. Army's M270 multiple launch rocket system, introduced in the 1980s, could fire 12 227mm rockets in under a minute, each rocket having a range of 20 miles or more and carrying a 200-pound warhead. Tactical missiles offered even greater range and precision. By the time precision-guided munitions became common in the 1990s, the idea of using a massive unguided howitzer shell to destroy a bunker seemed positively medieval. Yet the physics that made the Black Dragon effective remain unchanged. Kinetic energy mass times velocity squared still governs penetration of armor and fortifications. Modern anti-bunker weapons, from guided bombs to thermobaric missiles, rely on variations of the same principle. Deliver enough energy to a small enough area to overwhelm the structural integrity of the target. The 240mm shell achieved this through brute force 360 pounds at 2100 feet per second. Modern weapons achieve similar or better results through precision guidance and specialized warheads, but the underlying challenge remains: how to destroy a prepared defensive position occupied by a determined enemy. The human element of the story, Lieutenant Hayashi and his garrison inside their Class A bunker, represents the experience of countless soldiers throughout history who discovered that their fortifications were not as impregnable as they believed. Whether it was French knights behind castle walls facing English longbows, Confederate soldiers in trenches facing rifled artillery, German troops in bunkers facing British tanks, or Iraqi forces in bunkers facing American precision bombs, the pattern repeats. Engineering and bravery can create formidable defenses, but technological innovation eventually renders those defenses obsolete. For the Japanese defenders at Manila, the realization must have been psychologically shattering. The Imperial Japanese military placed enormous emphasis on fighting spirit, on willpower as a force multiplier that could overcome material disadvantages. The defensive positions in Intramuros represented not just engineering but commitment, the determination to hold at any cost, to extract maximum casualties from the enemy, to die rather than surrender. When those positions could be obliterated in 8 seconds by a single shell fired from 800 yards away, the commitment became meaningless. The fighting spirit could not reinforce concrete. Willpower could not deflect a 360-pound projectile. The material reality of modern warfare overwhelmed the ideology. This tension between ideology and material capability characterized much of the Pacific War. Japanese military doctrine emphasized offensive spirit, decisive battles, and acceptance of death. American military doctrine emphasized firepower, logistics, and preservation of American lives. When these two philosophies collided, the outcome was often devastatingly lopsided. At Manila, the Japanese achieved their goal of fighting to the death. Approximately 16,000 defenders perished. But they failed to significantly delay the American advance or extract proportional American casualties. The Black Dragon and similar weapons meant that American forces could reduce Japanese positions while minimizing American exposure to defensive fire. The civilian cost, however, was unconscionable. 100,000 Filipino civilians died in Manila, killed by Japanese massacres, American bombardment, or caught between the two forces. The 240mm shells fired into Intramuros certainly contributed to this toll, as did the 105mm and 155mm shells, the tank fire, the aerial bombardment, and every other weapon employed. The Americans argued that the quickest end to the battle would minimize overall casualties, but the speed of that end still came measured in weeks, and the civilian deaths still reached 6 figures. This raises uncomfortable questions that extend beyond the specific circumstances of Manila. When fortifications are built in urban areas, when defenders use civilians as shields, when battles become sieges, how does military necessity interact with humanitarian concern? The Geneva Conventions and later international humanitarian law have attempted to establish rules, but the fundamental dilemma remains. The 240mm howitzer was a tool, neither moral nor immoral in itself. Its use against Intramuros was justified by its operators as necessary to break a defense that otherwise might have lasted weeks longer. Its use was condemned by others as disproportionate, as applying excessive force in an environment where civilians were present. History has not rendered a final verdict on these questions, perhaps because there can be no final verdict. Each battle must be evaluated in its specific context. Manila in February 1945 was a specific situation, a Japanese garrison ordered to fight to the death, holding a city where they were also massacring civilians, against American forces determined to liberate the city as quickly as possible. The Black Dragon's 8-second destruction of bunkers shortened the battle, but at a cost measured in pulverized concrete, twisted steel, and shattered lives. For students of military history and technology, the M1 240mm howitzer remains a fascinating case study. It represents the apex of a certain type of artillery mobile enough to be field artillery, powerful enough to function as siege artillery. The Germans had their railway guns, massive weapons that required custom-built rail lines. The British had their super-heavy howitzers, equally immobile. The Americans, characteristically, built something that split the difference, heavy enough to destroy fortresses, mobile enough to be transported by trucks and tractors, deployable in hours rather than days. It was an engineering compromise that worked remarkably well within its design parameters. The gun's nickname Black Dragon proved prophetic. In Asian mythology, dragons are powerful, destructive, and often associated with transformation. The Black Dragon transformed fortress warfare, making static defense obsolete. It transformed the battle for Manila, breaking defenses that conventional artillery could not crack. And it transformed, in a small but significant way, the psychology of the Pacific War's final months. Japanese defenders at Okinawa and in the home islands, planning for an invasion that never came, incorporated the lessons of Manila. Build deeper, build underground, make every position expendable but every defense in depth. The weapon's ultimate obsolescence was inevitable. Technology moves forward. Rockets, missiles, and guided munitions replaced unguided heavy artillery for fortress warfare. But in that specific moment in 1945, when American forces faced concrete bunkers in an urban environment, when conventional artillery proved insufficient, when speed was essential in that moment, the Black Dragon was the right tool for a terrible job. 8 seconds, the time for a 360-pound shell to travel 800 yards and destroy a bunker that had been engineered to be indestructible. 8 seconds during which physics, engineering, and human lives converged in violence. 8 seconds represented the culmination of years of weapons development, the application of lessons learned across 2 world wars, and the brutal efficiency of industrial warfare. The men who fired the Black Dragon, the 22-man crews who loaded the shells, adjusted the elevation, pulled the lanyards, were doing their jobs as trained artillerymen. They calculated ranges, accounted for wind and temperature, adjusted fire based on observation, and fired for effect. They likely never saw the targets they destroyed except as coordinates on a map or instructions from a forward observer. Modern warfare frequently interposes distance between combatants, and artillery exemplifies this distance. The crews could perform their technical duties without confronting the human consequences of each shell. The men who died in those bunkers, Lieutenant Hayashi and thousands like him throughout Intramuros, were also doing their jobs as soldiers. They had been ordered to defend Manila to the death. They had built the best positions they could. They had prepared for siege, conserved ammunition and supplies, and established fields of fire. They had done everything their training and their engineering knowledge suggested. It was not enough against a weapon they had not encountered before, designed specifically to defeat fortifications like theirs. And between the artillerymen and the defenders were the civilians, 100,000 Filipino men, women and children, who became casualties of a battle fought in their city. Many were deliberately killed by Japanese forces in documented atrocities. Many died in the bombardment necessary to dislodge those forces. The 240mm shells crashing into Intramuros did not distinguish between military and civilian structures, between bunkers and buildings, between soldiers and refugees. The specifications called for destroying fortifications, and that is what the shells did. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.